So again, I don't know really how to address that question. I say this is not the most difficult material. It will be for this semester, just from not just my observations, but experiences, okay? Then when we get to the spring, when we get to the biochemistry portion, some people may say that that is more difficult to understand or comprehend. Because when it comes to that of organic chemistry, I think it's just more concepts that you need to keep straight, because you're not just naming compounds with organic chemistry, you also have the reactions that accompany them. And that's the difficult part for what the seniors are working through now. Okay, so I would say enjoy this time while we can. And we'll ask Mr. Wagner this. To me, I've always approached this saying this is the entire backbone of what general chemistry is, okay? Now, is there other concepts that go with general chemistry, like titrations? Yes. Like dealing with pH solutions? Yes, there is. But this is more so comprehensive of everything that we've learned so far. How elements interact with one another, and also what we call conservation of some sort of atoms on the left-hand side or the reactant side with what's on the product side. And your next evaluation will include all that of classifying reactions and balancing them. Now, we don't get this complex. This would just be a total guess on your part, and if you wouldn't get it correct, I wouldn't expect anyone to, unless they just threw an answer out there that's not bizarre, but one you would not think of. So when we look at this equation, in the following reaction, we got aluminum oxide plus carbon plus nitrogen results in aluminum nitride plus carbon monoxide. How much carbon is needed to make 1,000 grams of aluminum nitride? So when we look at this type of reaction, okay, you're getting a little ahead of ourselves. If you had to guess, this is what we were saying earlier, I wouldn't expect anyone to get this right on what type of reaction this is, because it is so complex. For our purposes, this is a complex reaction. It can't be a double replacement, because you're not having two compounds being replaced. You really don't have anything being replaced. Someone said it earlier. Okay? More so a synthesis reaction, because we're taking substances to see how much of what we actually need. Now, aluminum nitride, this is a type of substance that can withstand heat, okay, but yet be a transistor. It can still conduct electricity, but it doesn't get overly hot, okay? So that's something that might be very important for a chemical company like we were talking earlier, maybe like DuPont or Purdue or Eli Lilly or Procter & Gamble. Those are all American corporations that deal heavily with research in chemistry. So with this, a lot of you were already 3 steps ahead when, oh, we got a little bit of this, a little bit of this to balance this out. And one of the things that we would say, it's just trial and error, okay? So as you approach this, probably the most logical place to start would be here. I'm not saying that that's correct, but why would that be the most logical place to start? Because you have 2 aluminums on the left side. So by trial and error, let's see once what happens. Your aluminums are balanced. What else is balanced? Your nitrogen is also balanced, okay? Now, when we look at this, we've got 3 oxygens to only 1 over here. So Put a 3 here, and then the $100 question, where do we end? Putting a 3 here. Now, what stoichiometry does is allows you to jump from one side of the reaction to the other, okay? Because everything that we've done up to this point was composition stoichiometry. In other words, what that might say is if we had 1,000 grams of aluminum nitride, how much of that is aluminum? And you can't say it's a 50-50 split. With very little knowledge of this, why can we not say that 50% or 500 grams is aluminum and 500 grams is nitrogen? Because they have different masses, so it can't be a 50% split between the two. It might be 65 and 35. That might be a little more applicable. But that's composition stoichiometry. When you talk about reaction type, you have to have a chemical reaction involved, and that's what we see here. So why would a chemist want to be so precise about this? Well, if you need to make sure that you have 1,000 grams of this being produced, you better make sure that you start with enough of this substance, okay? So this is built upon some prior knowledge. So bear with me as we go down this road here. There's only one place we can start, and that's 1,000 grams of this aluminum nitride. So we need to know how much carbon. When we say how much carbon, that's going to be measured in what? It's going to be measured in grams. So what that means is we are going to convert 1,000 grams of this, actually I put the arrow the wrong way, to how many grams of this carbon is needed. Okay, so bear with me and take a deep breath. Okay. You start on the product side because we want to make sure that we produce 1,000 grams of this aluminum nitride. Now we can do that even, it's not much more work to put an L in there, but if you just put A and N, that would be fine because it's just aluminum nitride. Excuse me. Okay, now every time that we see something measured in grams, we're going to probably change it to what? Okay, so how do we get rid of this gram in this next step? Because you said you're going to change it to moles. You're right when you say that. But does that go on the top or the bottom? Okay, so grams of aluminum nitride will give you a mole of aluminum nitride. Okay, so we just don't pull a number out of the air to put there. You already said it. So what, 27 in 14, is that 41?
That sounds about there.
Well, 0.01, I guess. 41.01. And that's just the atomic masses of those two elements put together. We are now in moles of aluminum nitride. This is how it was different with your composition stoichiometry. You just stayed within one compound. Here, we're going from one compound to another, and that's what this mole ratio allows you to do. Because when we look at a mole ratio, how do we get rid of this moles of aluminum nitride? Well, it's either one or the other. If you multiply it, you're squaring it. Okay, so we're going to put moles of aluminum nitride here. So this is going to allow us to jump from this side of the reaction to this side. So it allows us to change what we have into what it is that we're looking for, which is It's essentially grams of carbon, but we have to go through moles first. Because from chapter 7, in this third step, we said it was so important. We said it allows you to change what you have, which was moles of the entire compound, to just moles of whatever element you're looking for in there. Because you're not changing substances, you're just within the same compound. That is the difference between what we had done in chapter 7 and what we're doing here. Now, the last thing you need to do is go back to your chemical reaction now. Okay? There's got to be something significant on why you have to balance it first, which there is. Once you refer to your reaction, how many moles of aluminum nitride are there? You're right, but why are you right? Because that is from this coefficient up here. That's why we said when it comes to doing stoichiometry, if you are not good at balancing chemical reactions, you just can't do this process. You just can't, because these numbers are so important here. So what do we see in front of the mole of carbon?
3.
So it's a 3-to-2 ratio because of this number and this number. So now we've got all this gone. We're in moles of carbon, but we don't want moles. What do we want instead? Grams. So how do we take this the rest of the way home?
Put 12.01 on the bottom or on the top. Yeah, on the top.
Okay, I like the top better. In this instance where you say put that number on top. Now you laugh all you want, but people are going to do this. Why not?
You already got rid of it.
Right, the only time you should see a number in front of the moles is if you have a mole ratio, when you have moles over moles. Sometimes it's 1, okay? So if we were dealing with nitrogen, it would just be a 1 in front of there. But you have to go by the coefficients. And then, so just out of curiosity, Mr. Wagner, any of your classmates that you went to college with, did they not take chemistry in high school, but had to in college, that you're aware?
Not the same chemistry section. There was a section that's slightly below.
Okay. So I would believe that would be awful, trying to learn this without having any exposure to it.
Don't you have to take a chemistry class or
In high school? No.
I guess
You could take a zoology class, yes. Yep. But that was from a prior discussion. We all made the commitment to be in here. We're glad we're here, right? Because this is so much fun, right?
Yep.
We like the enthusiasm. Okay, so when numbers are next to one another, what do we do?
Multiplying.
Okay, same as on top as on the bottom. If you have numbers, then at the end, divide the two. Okay, so 3,000, taking a shortcut by just multiplying these two, 3,000 times, that probably gives you, what, 36,000, okay? Times 12.01 is 36,030. Then divide that by 82.02, because these two multiplied is 82.02. And you need 439.28. Grams of carbon. Okay? Now, one of the, I'll keep this short, one of the facts about landing on the moon back in the Apollo 11 mission, I think is when it was. And I think we talked about this in physical science. Who in their right mind would want to go to the moon? Okay? Now, think about the technology at that time was pretty well advanced in the 1960s. But the idea behind that was, once you land on the moon, if those booster rockets don't fire up, you're stranded there. There really is no technology to pick up a satellite phone and say, come pick us up. But the idea behind that was, it was a chemical reaction that fires up those booster rockets. So you'd have to be a chemist. The point behind that is, I'm sure that if this was a reaction, we do talk about booster rockets in a stoichiometry problem later on down the line, but the idea behind that is, I'm sure these numbers are triple checked, because if that chemical reaction did not take place, those 3 astronauts probably, I'm not saying that they would have died there, but they would have been stuck there for a long time.
They just have to jump off the moon. That's where you just take your suit off.
You can't be serious.
I mean, I wouldn't want to be up there for that long. They just have to jump off the moon.
If you jump off the moon, will you land on Earth?
No.
Sometime.
No. My perception of that would not be the case, because you have to take into account, do you have any idea how fast we are spinning right now? 22,000 miles an hour. That's how fast the Earth is moving. But we just don't feel that because the mass of the Earth is so big. But the idea behind that is to try to hit that type of a moving target. Sorry, Mr. Wagner, I know you're a good shot with your deer hunting abilities, but being an astronaut, I don't think you're that good of a shot.
Aim small, miss small.
Aim small, miss small. Good advice. Okay, so what about 1,000 miles per hour? I don't think that's right.
Yep.
Okay. All right. So this is some of the content that we'll be doing when you come back from Thanksgiving break, okay? Because next week we'll be working on your next evaluation, which is just balancing and classifying reactions. So we will catch up to you next time. Any final thoughts for our ladies?
Good luck. Good luck.
Good luck, we hear. What else?
They're the best ever.
Better win.
Okay, they're the best ever. They're going to win.
And don't do drugs.
Drive safe.
I think they know that.
Be safe out there. Be safe.
Okay, be safe out there.
Don't do drugs.
And best wishes. We'll catch up to you next time.